Introduction to Mobile Architecture. Mobile architecture refers to the structural design and organization of software and hardware components within mobile devices and applications. It encompasses everything from the operating system and user interface to data storage, networking capabilities, and security protocols. Understanding mobile architecture is crucial for developing efficient, scalable, and secure mobile applications that meet user expectations. This field continuously evolves, driven by advancements in hardware, software, and connectivity technologies. A well-designed architecture ensures optimal performance, reliability, and maintainability of mobile solutions. It also dictates how an application interacts with the device's resources and external services. Effective mobile architecture is the backbone of successful mobile experiences. Evolution of mobile devices. The journey of mobile devices began with rudimentary car phones and brick-like cellular phones in the 1980s, primarily used for voice communication. Over time, these devices shrank in size and gained basic text messaging capabilities, becoming more accessible to the general public. The early 2000s saw the rise of feature phones, introducing cameras, color screens, and limited internet access, paving the way for more sophisticated functionalities. The true revolution arrived with smartphones, combining powerful computing, advanced operating systems, and touch interfaces, transforming devices into portable computers. This evolution has been marked by continuous innovation in processing power, display technology, battery life, and connectivity options. Each generation brought significant improvements, expanding the possibilities for mobile applications and user interaction. Today's mobile devices are indispensable tools, integrating seamlessly into daily life. Mobile operating systems. Mobile operating systems, OS, are the software platforms that manage mobile device hardware and software resources, providing common services for mobile applications. The two dominant players in this space are Apple's iOS and Google's Android, each with distinct architectures and ecosystems. iOS is known for its closed ecosystem, tight hardware-software integration, and strong emphasis on security and user privacy. Android, conversely, is open source, offering greater flexibility and customization options across a wide range of devices from various manufacturers. Other operating systems, like iOS and older platforms such as Windows Phone or BlackBerry OS, have niche markets or have largely faded. Developers must consider the target OS when designing and building mobile applications, as each platform has specific guidelines, development tools, and user interface conventions. The choice of OS significantly impacts the development process and the application's reach. Core components of mobile devices. Mobile devices are sophisticated pieces of engineering, integrating numerous core components to deliver their functionality. At the heart is the System on a Chip, SoC, which typically includes the Central Processing Unit, CPU, Graphics Processing Unit, GPU, and memory, acting as the device's brain. Displays, often touch-sensitive, provide visual output and user input, varying widely in technology from LCD to OLED. Batteries are critical for portability, with continuous advancements focusing on energy density and charging speed. Various sensors, such as accelerometers, gyroscopes, magnetometers, and proximity sensors, enable context awareness and advanced interactions. Connectivity modules for Wi-Fi, Bluetooth, GPS, and cellular networks ensure seamless communication. Cameras, microphones, and speakers facilitate multimedia capture and consumption. These components are meticulously integrated to create a compact, powerful, and versatile device, each playing a vital role in the overall mobile experience. Mobile application types. Mobile applications are broadly categorized into three main types: native, hybrid, and web applications. Each type offers distinct advantages and disadvantages, in terms of performance, development cost, user experience, and platform reach. Native applications are built specifically for a single mobile operating system, leveraging the device's full capabilities and offering the best performance and user experience. Hybrid applications are developed using web technologies, HTML, CSS, JavaScript, and then wrapped in a native container, allowing them to run on multiple platforms with a single codebase. Web applications, often progressive web apps, PWAs, are essentially websites designed to be highly responsive and function like an app when accessed through a mobile browser, without requiring installation from an app store. The choice of application type depends heavily on project requirements, budget, target audience, and desired functionalities. Understanding these distinctions is fundamental for making informed architectural decisions. Understanding native applications. Native applications are developed using programming languages and tools specific to a particular mobile operating system, such as Swift, Objective-C for iOS, or Kotlin, Java for Android. This approach allows direct access to all device hardware features, including cameras, GPS, accelerometers, and local storage, without any performance overhead. As a result, native apps typically offer the highest level of performance, responsiveness, and the most seamless user experience, closely adhering to platform-specific UI/UX guidelines. They can fully leverage the native UI components and design patterns, providing a familiar and intuitive feel for users. However, developing native applications means maintaining separate code bases for each platform, which can increase development time and cost if targeting both iOS and Android. Despite this, for applications requiring intensive graphics, complex animations, or deep hardware integration, native development remains the preferred choice, delivering unparalleled quality and speed. Exploring hybrid applications. Hybrid applications combine elements of both native and web applications. They are built using standard web technologies like HTML, CSS, and JavaScript, similar to a website. However, instead of running in a mobile browser, they are wrapped inside a native container using frameworks such as Apache Cordova, Ionic, or React Native. This container allows the web-based application to be packaged as a native app and distributed through app stores. A key advantage of hybrid apps is code reusability, allowing developers to write once and deploy to multiple platforms, iOS and Android, significantly reducing development time and cost. While they offer access to some native device features through plugins, their performance might not always match that of truly native applications, especially for graphics-intensive tasks. Hybrid apps strike a balance between development efficiency and native functionality, making them a popular choice for many business applications and MVPs. Web applications for mobile. Web applications for mobile are essentially websites optimized for mobile devices, accessed through a web browser. They do not require installation from an app store and are platform independent, meaning they run on any device with a compatible browser. Progressive web apps, PWAs, represent an advanced form of mobile web applications, offering enhanced capabilities that bridge the gap between traditional web and native apps. PWAs can be installed to the home screen, work offline, send push notifications, and access some device features, providing a more app-like experience. They are built using standard web technologies, HTML, CSS, JavaScript, and benefit from faster development cycles and easier updates. While PWAs offer broad reach and lower distribution friction, they generally have limited access to device hardware compared to native or even hybrid apps. The focus for mobile web apps is on accessibility, discoverability, and a consistent experience across various devices and screen sizes. Mobile development environments. Mobile development environments consist of integrated development environments, IDEs, and software development kits, SDKs, that provide the necessary tools for building mobile applications. For iOS development, Xcode is the official IDE, offering a comprehensive suite of tools for coding, debugging, and UI design, along with the iOS SDK. Android Studio, based on IntelliJ IDEA, is the official IDE for Android, bundled with the Android SDK. Emulator and various development tools. These SDKs include libraries, APIs, documentation, and sample code specific to each platform, enabling developers to interact with device features. Cross-platform frameworks, like React Native and Flutter, also have their own development environments and command-line tools that integrate with native SDKs. Choosing the right development environment is crucial for developer productivity and the efficiency of the application development lifecycle. Familiarity with these tools is essential for any mobile architect or developer. Programming languages for mobile. The choice of programming language is a fundamental aspect of mobile architecture, directly impacting development efficiency, performance, and access to platform features. For native iOS development, Swift is the modern preferred language, known for its safety, performance, and expressive syntax, having largely replaced Objective-C. Android native development primarily uses Kotlin, a modern, concise, and interoperable language that runs on the Java virtual machine, alongside Java, which remains widely supported. For cross-platform development, JavaScript is extensively used with frameworks like React Native, allowing developers to write mobile apps using web technologies. Dart, developed by Google, is the language behind Flutter, known for its fast development cycles and excellent performance. Each language comes with its own ecosystem, community support, and learning curve. Mobile architects must select languages that align with project goals, team expertise, and long-term maintenance strategies, as this decision underpins the entire technical stack. User interface, UI design principles. User interface, UI design for mobile applications focuses on the visual elements and interactive components that users engage with. Key principles include clarity, consistency, and efficiency. Clarity ensures that all UI elements are easily understandable and their purpose is obvious to the user. Consistency in design across different screens and interactions helps users learn and navigate the app intuitively. Efficiency means enabling users to complete tasks with minimal effort and steps. Mobile-first design is a crucial approach, where the design process begins with the smallest screen size and then scales up to larger displays, ensuring core functionality is prioritized. Responsiveness and adaptability are also vital, allowing the UI to adjust gracefully to various screen dimensions, orientations, and input methods. Adhering to platform-specific UI guidelines, including platform-specific design. Apple's Human Interface Guidelines, Google's Material Design, is essential for creating a familiar and positive user experience. A well-designed UI is not just aesthetically pleasing, but also highly functional and user-friendly. User experience UX considerations. UX design focuses on the overall feeling and satisfaction the user has when interacting with a mobile application. It goes beyond the visual interface to encompass usability, accessibility, and emotional response. Key UX considerations include intuitive navigation, clear feedback mechanisms, and minimizing cognitive load. Gestures such as swiping, pinching, and tapping are integral to mobile UX, requiring careful implementation to be natural and predictable. Accessibility ensures that the app is usable by individuals with diverse abilities, incorporating features like voice control, larger text options, and screen reader compatibility. Performance, including fast loading times and smooth animations, significantly impacts UX. Slow or buggy apps lead to frustration. Contextual awareness, leveraging device sensors to provide relevant information or actions, also enhances the user experience. A successful UX design creates a delightful and efficient journey for the user, making the app enjoyable and valuable. It is about understanding user needs and behaviors to craft a meaningful interaction. Data storage on mobile devices. Effective data storage is a critical aspect of mobile architecture, balancing performance, security, and user experience. Mobile applications often need to store data locally on the device for offline access, faster retrieval, or to persist user preferences. Common local storage options include shared preferences for key value pairs, SQLite databases for structured data, and internal, external storage for files like images or documents. Each method has specific use cases and security implications. Cloud storage, on the other hand, allows data to be stored remotely and synchronized across multiple devices, offering scalability, backup, and real-time collaboration features. Services like Firebase, AWS Amplify, or custom backend APIs provide robust cloud storage solutions. Architects must carefully consider data sensitivity, volume, access patterns, and offline requirements when choosing between local, cloud, or a hybrid approach to data storage. Proper data management ensures application reliability and user data integrity. Networking and connectivity. Mobile applications heavily rely on networking and connectivity to interact with backend services, fetch data, and communicate with other devices. This involves various protocols and technologies, including Wi-Fi, cellular data, 3G, 4G, 5G, and Bluetooth. RESTful APIs are the most common method for mobile apps to communicate with servers, enabling data exchange in formats like JSON or XML. Efficient network communication is crucial for performance, as slow or unreliable connections can severely degrade the user experience. Mobile architects must design for varying network conditions, implementing strategies like caching, data compression, and retry mechanisms to handle intermittent connectivity. Offline support, allowing users to continue using core app functionalities without an internet connection, is also a key consideration. This often involves synchronizing data when a connection becomes available. Secure communication, typically through HTTPS, is paramount to protect data in transit. Robust networking ensures that mobile apps remain functional and responsive in diverse environments. Security in mobile architecture. Security is a paramount concern in mobile architecture, given the sensitive data often handled by mobile applications and the inherent vulnerabilities of mobile devices. A robust security strategy encompasses multiple layers, from secure coding practices to data encryption and authentication mechanisms. Common threats include malware, phishing, insecure data storage, insecure communication, and reverse engineering. Best practices involve implementing strong user authentication, introduction, multi-factor authentication, encrypting all sensitive data both at rest and in transit, and validating all input to prevent injection attacks. Regular security audits and penetration testing are essential to identify and mitigate vulnerabilities. Protecting against reverse engineering through code obfuscation and tamper detection helps prevent malicious actors from understanding and exploiting the application's logic. Mobile architects must design with security in mind from the outset, ensuring that the application and its data are protected throughout their lifecycle. A proactive approach to security is vital for maintaining user trust and compliance. Performance optimization in mobile architecture is critical for delivering a smooth and responsive user experience, directly impacting user satisfaction and retention. Key areas for optimization include battery usage, memory management, and application speed. Minimizing battery consumption, involves efficient use of background processes, location services, and network requests. Effective memory management prevents crashes and sluggishness by releasing unused resources and optimizing data structures. Application speed is enhanced through efficient algorithms, optimized image and asset loading, and reducing network latency. Techniques like caching data, lazy loading, and code splitting can significantly improve startup times and overall responsiveness. Profiling tools provided by development environments help identify performance bottlenecks, such as CPU spikes or excessive memory usage. Continuous monitoring and iterative optimization throughout the development lifecycle are essential. A high-performing mobile application feels fluid and instantaneous, making it a joy to use. Prioritizing performance ensures a superior user experience. Testing mobile applications. Thorough testing is an indispensable part of mobile application development, ensuring quality, stability, and a positive user experience. Various types of testing are employed, each addressing different aspects of the application. Unit testing focuses on individual components or functions of the code, verifying their correctness in isolation. Integration testing checks the interactions between different modules or services, ensuring they work together as expected. UI testing, or instrumentation testing, simulates user interactions to verify that the user interface behaves correctly across various devices and screen sizes. Performance testing evaluates the app's responsiveness, stability, and resource usage under different loads. Security testing identifies vulnerabilities and ensures data protection. Usability testing involves real users to gather feedback on the app's ease of use and overall experience. Automated testing frameworks and continuous integration pipelines are crucial for efficient and repeatable testing processes. Comprehensive testing minimizes bugs, improves reliability, and ultimately delivers a higher quality product to users. Deployment and distribution. Deployment and distribution are the final steps in bringing a mobile application to its users, involving packaging the app and making it available through various channels. For public applications, the primary distribution channels are official app stores, Apple App Store for iOS, and Google Play Store for Android. This process involves adhering to each platform's strict guidelines, submitting the app for review, and managing updates. Enterprise applications, intended for internal use within an organization, can be distributed through mobile device management (MDM) solutions or private app stores, bypassing public review processes. The deployment process includes signing the application with developer certificates, bundling all necessary assets, and preparing release builds. Continuous integration, continuous deployment (CI/CD) pipelines automate these steps, ensuring consistent and rapid releases. Effective distribution strategies are crucial for reaching the target audience and ensuring users have easy access to the latest versions of the application. Understanding the nuances of each distribution channel is vital for a successful launch. Backend integration for mobile. Backend integration is essential for most modern mobile applications, providing server-side logic, data storage, user authentication, and other services that cannot be handled solely on the device. This typically involves connecting the mobile app to a backend server through APIs, most commonly RESTful or GraphQL. The backend can be custom-built using frameworks like Node.js, Python Django, or Ruby on Rails, or it can leverage backend as a service (BaaS) platforms. BaaS solutions such as Firebase, AWS Amplify, or Azure mobile apps provide pre-built backend functionalities like databases, authentication, and cloud functions, significantly accelerating development. Mobile architects must design efficient and secure API endpoints, considering data formats, authentication protocols, and error handling, optimizing API calls for mobile environments. including minimizing payload size and supporting offline synchronization, is crucial for performance. A robust backend ensures that the mobile application can scale, manage complex data, and provide a rich feature set to users. It acts as the central hub for all data and logic not residing directly on the device. Cloud services for mobile apps. Cloud services have become indispensable for modern mobile applications, offering scalability, flexibility, and a wide array of functionalities without the need for managing physical infrastructure. These services provide solutions for backend hosting, data storage, user authentication, push notifications, analytics, and more. Major cloud providers like Amazon Web Services, AWS, Google Cloud Platform, GCP, and Microsoft Azure offer specialized mobile development services, such as AWS Amplify, Firebase, and Azure Mobile Apps. These platforms simplify backend development by providing ready-to-use APIs and SDKs, allowing developers to focus on the client-side experience. Leveraging cloud services enables applications to handle fluctuating user loads, store vast amounts of data, and deliver real-time features efficiently. Mobile architects must select cloud services that align with the application's requirements, budget, and scalability needs. The strategic use of cloud resources can significantly enhance an application's capabilities and reduce operational overhead. Cloud services empower mobile apps to be more robust and feature-rich. Cross-platform development frameworks. Cross-platform development frameworks allow developers to write a single code base that can be deployed across multiple mobile operating systems, primarily iOS and Android. This approach offers significant advantages in terms of reduced development time, lower costs, and easier maintenance compared to native development. Popular frameworks include React Native, Flutter, and Xamarin. React Native, based on JavaScript, enables developers to build native mobile apps using a declarative UI paradigm similar to web development. Flutter, developed by Google and using Dart, is known for its fast development, expressive UI, and excellent performance, often approaching native levels. Xamarin, a Microsoft product, uses C# and allows for shared code across platforms while still accessing native APIs. While these frameworks offer efficiency, they might introduce certain limitations regarding access to specific native features or performance for highly complex applications. The choice of framework depends on factors like team expertise, project requirements, and desired performance characteristics. Cross-platform solutions are increasingly popular for their ability to deliver applications to a broader audience more quickly. Mobile Device Management, MDM. Mobile Device Management, MDM, is a crucial aspect of mobile architecture within an enterprise context, focusing on securing, monitoring, managing, and supporting mobile devices deployed across an organization. MDM solutions allow IT administrators to enforce security policies, configure devices, distribute applications, and remotely wipe data if a device is lost or stolen. Key functionalities include device enrollment, inventory management, application management, MAM, content management, MCM, and remote troubleshooting. MDM helps organizations maintain compliance with security regulations, protect sensitive corporate data, and ensure employee productivity. It provides a centralized platform for managing a diverse fleet of mobile devices, regardless of operating system or manufacturer. Implementing MDM requires careful planning to balance security needs with user experience and privacy concerns. As mobile devices become increasingly integral to business operations, robust MDM strategies are essential for maintaining a secure and efficient mobile environment. It is a cornerstone of enterprise mobility. Emerging trends in mobile. The mobile landscape is constantly evolving, with several emerging trends shaping the future of mobile architecture. 5G connectivity is revolutionizing mobile experiences by offering ultra-fast speeds and extremely low latency, enabling new applications in areas like augmented reality (AR) and virtual reality (VR) and real-time streaming. Artificial intelligence (AI) and machine learning (ML) are being integrated into mobile devices and applications for features like intelligent assistance, personalized recommendations, advanced image processing, and on-device inference. The Internet of Things (IoT) is increasingly converging with mobile, allowing smartphones to act as central hubs for controlling smart home devices, wearables, and industrial IoT sensors. Edge computing is gaining traction, pushing computation closer to the data source, the mobile device itself, to reduce latency and improve privacy. These trends demand mobile architectures that are more powerful, efficient, and interconnected, capable of handling complex data processing and real-time interactions. Staying abreast of these developments is crucial for future-proofing mobile solutions. Monetization strategies for mobile apps. Monetization strategies are a critical consideration in mobile architecture, determining how an application generates revenue and sustains its development. Various models exist, each with its own architectural implications. Paid apps require users to purchase the application upfront, often relying on a strong value proposition and marketing. Freemium models offer a basic version of the app for free, with advanced features or content available through in-app purchases or subscriptions. In-app advertising integrates ads into the application, generating revenue based on impressions, clicks, or video views. Subscriptions provide recurring revenue by offering access to premium content or features for a set period. In-app purchases allow users to buy virtual goods, extra lives, or unlock specific functionalities. Mobile architects must design the application structure to seamlessly integrate the chosen monetization model, ensuring a smooth user experience while maximizing revenue potential. This often involves robust backend systems for transaction processing, subscription management, and analytics. The chosen strategy influences the entire app design, from user flow to data tracking. Future of mobile architecture. The future of mobile architecture is poised for continuous innovation, driven by advancements in artificial intelligence, ubiquitous connectivity, and immersive user experiences. We can expect deeper integration of AI and machine learning directly on devices, enabling more personalized and context-aware applications with enhanced privacy. The proliferation of 5G and future wireless technologies will unlock new possibilities for real-time data processing, edge computing, and seamless interaction with IoT ecosystems. Augmented reality (AR) and virtual reality (VR) will become more mainstream on mobile platforms, demanding architectures capable of handling complex 3D rendering and sensor fusion. Security will remain a critical focus, with increased emphasis on hardware-level security. Biometric authentication and privacy-preserving technologies. Cross-platform development will likely continue to evolve, offering even closer to native performance and broader access to device capabilities. Mobile architectures will need to be increasingly adaptive, resilient, and intelligent to support the next generation of mobile experiences. The convergence of various technologies will redefine what a mobile device and mobile application truly mean. Conclusion. Key takeaways. This course provided a comprehensive introduction to mobile architecture, covering its fundamental concepts and evolving landscape. We explored the different types of mobile applications, native, hybrid, and web, understanding their unique characteristics and use cases. The importance of mobile operating systems, core device components, and programming languages was highlighted as foundational knowledge. Key architectural considerations such as UI, UX design, data storage, networking, and robust security measures were discussed in detail. We also examined the critical role of performance optimization, thorough testing, and effective deployment strategies in delivering successful mobile products. Finally, the course touched upon the integration of backend and cloud services, along with emerging trends and a future trajectory of mobile technology. The insights gained here form a solid basis for further specialization in mobile development or architectural roles. A strong grasp of these principles is essential for anyone looking to build or manage mobile solutions in today's digital world.